Wishing you all. I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I wish to tell about the body centered cubic crystal structure. Body centered cubic crystal structure. Okay. So in this BCC structure, we are going to see the characteristics of the BCC structure. Body centered cubic structure. Body centered cubic structure. So in this, what are the characteristics? So the characteristic, what type of cell it is, what type of unit cell it is, and whether it is primitive or not, and what are the effective number, that is total number of atoms in the unit cell. We call it as effective number of atoms in the unit cell, and then atomic packing factor, coordination number, so interstitial space. So these are all the characteristics we are going to see about the body centered cubic structure. So first we can see that in the unit cell of body centered cubic structure, it has one atom at each corner, one atom at each corner. In unit cell of BCC structure, it has one atom at each corner and one at the center of the cube. So along with the each corner atom, there is one more atom which is at the middle of the body. That is middle of the body's middle of the cube. Okay, so the corresponding parameters for BCC structure, or we are going to see the parameters: unit cell, primitive cell, whether it is primitive cell or not, and effective number of atoms in unit cell, and then coordination number, atomic radius, and then we are going to see the packing factor, nearest to neighboring distance. This is atomic packing factor, and how much the space is there. So here in a body centered cubic structure, as I said, along with the corner atoms, there is one more atom at the middle of the cube. Okay, so here the unit cell type is cubic unit cell. Cubic unit cell, and it consists of a center of atom along with the corner atoms. So it is not primitive cell. So what is the primitive cell? What is the condition? What is the primitive cell? Means that the primitive cell is a unit cell which has only one lattice point, which has only one lattice point in the unit cell. So that we call it as a primitive unit cell or primitive cell. So here when we see about the cube, if we see the cube, so these are the corners. So in each corner atoms are there. So at each corner atoms are there. Along with this corner atoms, so 8 corners are there. 1, 2, 3, 4, 5, 6, 7, 8. So 8 corners are there. And along with the 8 corners, there is one more atom at the middle of the cube. At the middle of the cube. So in this unit cell, along with the corner atoms, there is one more atom which is at the middle, so that the total number of atoms is 2. So that it is made up of 2 lattice points, so that it is not primitive. If the lattice points are only 1, then it is primitive unit cell. But it is 2. There is here in this cube, body centered cube, the lattice points are 2, so that it is not primitive. So it consists of a center of atom along with the corner atoms, so it is not a primitive unit cell. And effective number of atoms in the unit cell. Effective number of the atoms in the unit cell. So in BCC unit cell, each and every corner atoms is shared by 8 adjacent unit cells. 8 adjacent unit cells. So the total number of atoms contributed by the corner atoms is 1 by 8 into 8. So this 1 by 8 is the sharing of the atom with the adjacent unit cell atoms. So here also at 8 corners. So here in the left, back, and this side, and down, and up, and front, and back. So 8 unit cells. So if we take, this is a unit cell of a crystal. This is a unit cell of a crystal. In this, there is 8 corners of this cube. There is 8 corners in this cube. These 8 atoms, which are at the corner, be shared with the adjacent unit cells atoms. Adjacent unit cells corner atoms. Okay. So this corner atom be divided into 8. So corner atom divided into 8, and here also corner atom is divided into 8 because 8 adjacent unit cells we shared this atom, and here also 1 by 8. So each corner atom is shared by 8 adjacent unit cells atoms. So each corner have 1 by 8th share of a atom. 1 by 8th share of the atom. So totally 1 by 8 into 8 is equals to 1. So effective number of atom only at the corner is 1. A BCC unit cell has one full atom which is at the center of the unit cell. Along with the each corner, we said that at the middle of the unit cell, there is one more atom. So the effective number of atoms present in body centered cubic unit cell is 2. So these are corner atoms. All these 8 corner atoms will gives one atom, and along with that middle we have one more atom. So this one atom. So we are getting 1 by 8 into 8 each corner atom. So 1 by 8 share. So 8 corners. So 1 by 8 into 8. So getting 1 atom, and along with that at the center one full atom. So 1 plus 1. So total number of atoms are 1 plus 1, 2. So the BCC unit cell contains 2 atoms. Okay. So next, coming to the coordination number. So let we consider a body centered atom. The nearest neighbor for a body centered atom is the nearest neighbor for a body centered atom is surrounded by 8 corner atoms. So therefore the coordination number of a BCC unit cell is 8. Okay, suppose here So we are considering body centered atom. So in this cube, this is body centered atom. This is body centered atom. So considering this body centered atom, what are the nearest neighboring atoms? So how many nearest neighboring atoms are there regarding to this or considering to this body centered atom? Body centered atom. So we already discussed about that nearest neighboring distance and coordination number. So which are at the nearest neighboring means which are at 2 hour distance. Okay. So here the nearest neighbor for a body center, the nearest neighbor for a body centered atom is surrounded by 8 corner atoms. So the coordination number of a BCC unit cell is 8. So considering this centered atom, the nearest neighboring to here and to here, here. So all 8 corners be at 2 hour distance. All be at 2 hour distance. Okay. So the coordination number of a BCC unit cell is 8. Okay. So considering the center of the atom, then what are the how many number of atoms are there at 2 hour distance? 2 hour distance, if we calculate, we'll get 8 corners, 8 atoms are being at 2 hour distance with the center atom. Center atom. From the center of the atom, these 8 corner atoms be at 2 hour distance. So totally 8 coordination number. Coordination number is 8. Next, coming to the atomic radius. So for a body centered cubic unit cell, the atomic radius can be calculated from this diagram. So here we can see there is 1/8 share of atoms at each corner. 1/8 share, and here to here is r distance atomic radius r. So already I told here to here the edge length is a. Okay, so we are considering this atom, center of the atom. So from the center of the atom, the nearest atom to this is, that is, it is a 2 hour distance. So this is also at 2 hour distance. This is also 2 hour distance here. Likewise, in the back side also we have 2 hour distance from the center of the atom. Okay, that's why we are getting effective number of that's why we are getting coordination number is 8. Coordination number is 8. Coordination number of BCC is 8. So atomic radius is nothing but half of the distance of nearest neighboring atom. Half of the distance of nearest neighboring atom. So nearest neighboring atom, we'll see the atomic radius. So here to here, the atomic radius, what we say, atomic radius is the half distance nearest neighboring atom. Half of the distance to the nearest neighboring atom, R. So here to here, R. So now we'll see that R value. We can calculate the atomic radius in the body centered cubic crystal. So here when taking the figure, here we have A, B, C, D. Each corner have atom in the cube. So AH is equals to 4R. Means that the atomic radius R, and here also for this atom R, this is of full atom, so 2R, so totally 4R, so that AH is equals to 4R, and CB is A, so the edge length is A. The edge length is A. We can take it as HD or AB or a DH. We can say DH is equals to A. DH is equals to A. Edge length DH is equals to A. So now I am taking the triangle AHD. AHD. I am taking this triangle AHD. So from AHD triangle, AD square plus DH square is equals to AH square. So AD square is nothing but AB plus BD. Okay. So to find this AD square, first we want to know AD. So to find the AD, we are considering ABD. We are considering ABD. This triangle we are going to know about the AD value. We are considering ABD triangle. ABD triangle. This triangle is used to calculate the AD value. Okay. So from this ABD, AB square plus BD square is equals to AD square. So AB square and BD square is equals to AD square. So what is this AB? As this is a cube, all sides have the same dimensions A. That is, for a cube, A is equals to B is equals to C, and the interfacial angles alpha is equals to beta is equals to gamma, that is equals to 90 degrees. So to find AD, we are taking the triangle ABD. We are taking ABD. So from this, AD square is equals to AB square plus BD square. So AB is A. So AB square, BD is also A square is equals to AD square. So from this, 2A square is equals to AD square. 2A square is equals to AD square. Now AD is equals to root 2A. Now substitute this AD value in this equation 1. So that we'll have AD square plus DH square is equals to AH square. AD square plus DH square is equals to AH square. That is the first equation. So we are substituting the AD square. So AD square we got 2A square. So from this AD we got root 2A. But here AD square, so that 2A square plus DH square. DH square have the length A square. So A square. So DH, this one. DH is A. So DH square is A square. So 2A square plus A square is equals to AH square is 4R. Already we have noted. So AH is 4R. So AH square is equals to 4R whole square. So from this 16R square is equals to 3A square. Now the atomic radius for the BCC structure R is equals to root 3 by 4A. Root 3 by 4A. So this is the atomic radius for the body centered cubic crystal. Next, coming to the nearest neighbor distance. Nearest neighbor distance 2R. So already we calculated R value, atomic radius. So let's substitute in this 2R. So 2R is equals to 2 into R is equals to root 3 by 4A, which we calculated, and 2R, this is the nearest neighboring distance. So 2R is equals to 2 into root 3 by 4 into A. This is the nearest neighboring distance. Next, coming to the atomic packing factor. So atomic packing factor or packing fraction, so we call like that. So atomic packing factor of a body centered cubic unit cell can be calculated by knowing the how many atoms present in the unit cell and what is the volume of the atom and what is the volume of the unit cell. So if we know all these values, all these parameters, then we can substitute and can find the atomic packing factor. Atomic packing factor. As atomic packing factor equation is so atomic packing factor simply we can say APF. So it is equals to volume occupied by all the atoms in an unit cell is divided by volume of the unit cell. Or else we can write number of atoms in a unit cell into volume of the atom divided by volume of the unit cell. Okay, this is the formula for atomic packing factor. So to calculate this atomic packing factor, we should know number of atoms in the unit cell, and what is the volume of the atom. Next, volume of the unit cell. So here the number of atoms present in BCC is 2. The number of atoms present in a BCC unit cell is 2. As already told, along with the each corner atom, there is one more atom being at the center of the cube. It is full atom. It is full atom. So that the number of atoms present in the BCC unit cell is 2. Volume of one atom. So as it is a sphere, we are taking volume of one atom 4 by 3 pi r cube. 4 by 3 pi r cube. And volume of the unit cell, as we are taking cube. So all sides being the same length, so that a cube, volume of the unit cell is a cube. And atomic packing factor 2 into 4 by 3, 2 into 4 by 3 pi r cube by a cube. So this is the atomic packing factor formula. So that is, this 2 is the number of atoms in a unit cell 2, and volume of the atom is 4 by 3. APF. So I'm writing here. APF is equals to 2 into, this is the 2 is the number of atoms in a unit cell, that is BCC unit cell. 2 into volume of the atom is 4 by 3 by r cube divided by volume of the unit cell. So volume of the unit cell is a cube. Okay. So as we calculated r value, so this r value we got that root 3 by 4a. R is equal to root 3 by 4a. So this r value can be substituted in this APF, atomic packing factor, that is in the above equation. So we'll get 2 into 4 by 3 pi r cube is root 3 by 4 cube a cube. So you can write by r cube. This is all the same. So I'm writing in this way to understand easily. So a cube. Okay. So when calculating this value, we'll get the value is 0.68. Calculating this value, we'll get the value of atomic packing factor is 0.68. That is 68% of which we get this 8. So 0.68 means that 68% of atoms are occupied in BCC unit cell. In the BCC units. So remaining, that is remaining how much? So 32%. So 32% is free. So atomic packing factor is 0.68, and this shows 68% of the volume of the body centered cubic unit cell is occupied by atoms. So 68% only the atoms are occupied in the BCC unit cell. So that it is closely packed structure when compared to the simple cubic structure. So in simple cubic structure, there we got only the atomic packing factor of simple cubic crystal 0.52. So half of the unit cell is filled with the atoms and half of the percentage will be free in the simple cubic crystal. But here 0.68. So in that sense 68%. Here 52%, but here 68% in the BCC is filled with the atoms. Remaining are free. So that it is closely packed cubic structure when compared to the simple cubic structure. So that the interstitial space is 32% in the BCC structure. So these are all the characteristics of the body centered cubic crystal. Okay. In the next section, we see about the face centered cubic structure. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.